In the last video, we were talking about the reactions of alcohols and or reactions of water to make alcohols, at least, I should say. And in this video, we're going to talk about the reactions of alkenes with alcohols now, right? Yeah, so I can take an alkene and react it to water to make an alcohol, but I can also take an alkene and react it with alcohol as well to make something else. So what do we end up with? What is the reaction or the products here? Well, we'll talk about it. You know we're going to. And we're going to talk about the mechanism first. However, alkene is, again, a C double bond C with some free feet that hang out, whatever they are, don't matter. And I'm going to react it with an alcohol. It can be any type of alcohol. It doesn't matter. This R to the OH group. The OH group is what made it an alcohol, right? And we are going to form some type of product. I've got to know what it is. Okay, so folks, the story here is no different than anything else. And this is what I want you to remember. With H and halogen, we split it in half. And I said, H goes on one, halogen goes on the other. All right, then we moved on to water, and we split that in half. And I said, H goes on one, OH goes on the other. And then we have alcohols, and alcohols are written this way. But folks, we split it in half, and we split it in half right there. Because H goes on one, and O, not H this time, but OR, whatever it carries with it, goes on the other. That's what I mean. Organic is a process. That's how it should be. And we're learning a process, and we're applying that process to every reaction that we're introducing. And folks, this works no different than all of the other examples that we have talked about already. The only difference are the pieces that go on to that double bond. That's it. That's it. There's no more than that. Okay, so just like with water, if we take an alkene and react it with an alcohol, no reaction is going to happen here. Okay, just an alcohol on its own, it's not going to work. Again, the reason is very similar to water. Water was polar. Alcohols are polar. Alkenes are typically nonpolar that like organic solvents. Alcohols have a tendency not to be too organic-y. They have an organic piece, but they also have a polar piece. It's very hard for these two things to get together first before they can react and have a baby that we know as a product. All right, so that double bond alkene and the alcohol has to have a catalyst in order for this to work. And the catalyst is going to be the same catalyst that we used for the water. There's no difference. It has to be under acid conditions. Then we can get something. We can get something out of this because now we have a matchmaker once more. And the matchmaker is going to go in and it's going to say, hey, double bond, you need a break. Right? You need to break this relationship that you have there, and you need to kind of figure out to go on, kind of be independent almost, and not rely on that other carbon so much. And then it's going to go over to this alcohol group, and it's going to say, I'm going to kind of force you to get back into the dating scene. I'm going to force you to kind of get out there, meet new people, make new relationships, and you might just find your one and only if you do that. So this hydrogen plays the same role as what it did with water. It is a matchmaker, but more importantly, it is a catalyst. It speeds this reaction up. So in the beginning, it could get used up, but after that, it's going to get regenerated, and it goes right back to where it came from. And that is the definition of a catalyst. It does not get used up. It only speeds the reaction up, and that is it. All right, so short term, what do I want you to know? Before we talk about the awful mechanism, what do I want you to know with this? Folks, not surprising here. You should be able to tell me at this point, okay? I've got a double bond, and guess what? Double bond will break. There we go. Two sites of attachment opens up, one here and one there. And what do you think is going to go on? Well, hydrogen plays with other hydrogens, so hydrogen will go onto one spot. And then on the other side, it's whatever's left over. However big that molecule is, it doesn't matter. I bring everything. So that oxygen, that's where my split happened, right? So hydrogen goes onto one, and the split happened right there at that O. So that oxygen is going to get connected, and then it's going to bring with it whatever piece that it has. It could be a methyl group, it could be an ethyl group, it could be an isopropyl group, it could be a ring. It doesn't matter what it is. That oxygen will bring the entire thing to the party. Now, if I do this, I take an alkene and I react it with an alcohol that's been protonated with a little bit of acid. What I end up here is an R, O, R. The R group to the left is whatever is going to be here, this big kind of mushy conglomerate piece. That's my R group to the left. And then I also have an R group to the right-hand side of that oxygen. So what we end up making with these reactions are ethers. And once again, we know what the ether functional group is. We've talked about this before, back in lecture 3 or lecture 1, maybe 3. We also know how to name some of these ethers. We've IUPAC'd them. We've also common named them. All of that can come back in these examples. Not a problem there. And we've identified them and we got accustomed to them. That's why we did them way back when. And now we're doing a reaction with them. Now we're actually making them. And these are going to be products of an alkene reaction with alcohol under acid conditions. Now, before I go further, what I need to do is I need to give you the mechanism. We need to talk about how exactly this process works. Okay? What kind of steps are going to be involved in order to generate the products as they are? So let's start here. We'll do CH3, CH, double bond, CH2. And we're going to react with it, protonated alcohol. Well, down here to the side, I'm going to kind of write that out a little bit. Let's say that I use methanol, CH3OH. Meth for one carbon, so methyl alcohol, or methane, drop the E, add OL for methanol. That's the IUPAC name, and up above is the common name. So I'm going to take methanol, and I'm going to react with it some H plus for the acid. What do you think is going to happen? Use your words. Use what we talked about. The hydrogen is going to be attracted to this oxygen that has some free pairs of electrons because those are negative areas. And what we end up with is a CH3 with an oxygen that has a hydrogen and another hydrogen onto the picture. And this oxygen still has a free set of electrons, and that also means that that alcohol now is protonated with a positive charge. That's the only way that this process is going to work. It's just like with water. This is the way water worked. I had O with 2 H's. That time, that was the only difference. An extra hydrogen still went on. An extra hydrogen still created a positive charge, and it does it here too. There's no difference in it. So this alkene is going to be reacting with a protonated alcohol. I'm just going to draw it down here like that. That's going to be the very first step. We have to understand where that comes from. And again, if the acid is not present, that cannot form. If that cannot form, a reaction doesn't happen. It's as simple as that. So when these two things come together, I have a nucleophile that is my alkene. It wants to be neutral, and right now there's a negative source that's there. And I have an electrophile. That electrophile is coming from the protonated alcohol. Now I have the two sides of the story. They come together, they give me a perfect marriage, they can give me some products. Those products, we got to figure out what those babies are. We're going to have to draw those babies, and we're going to have to name those babies. How does that process happen? Well, you can probably predict it in a way. Curvy arrow mechanisms, we start at the negative source. There we are. We point it to the positive piece that we're going to rip off. All right, well, what's easily accessible, what is easily to be dumped by the curb that nobody likes, that nobody wants, it's the hydrogens. The hydrogens are always the first to go. So this oxygen knew. In the beginning, it was okay. And then the oxygen brought on another partner. And then it realized, uh-oh, there's no way I can keep up with all of these people. There is no way that I can keep this relationship going between three. Two was bad enough, but now I bring in a third? This ain't going to work. It's wearing me out to keep up with all of them. Okay, well, that oxygen realizes that, and it says, you know what? I made a mistake. I made a mistake bringing you in to my two relationships. So, hydrogen, you got to go. And if I get an opportunity to kick you to the curb, that's exactly what I'm going to do. So this double bond, which is a negative source, looks at that hydrogen and it says, hey, buddy, what you got going on right there, it's just not working for you. Oxygen wants you anyway gone. Oxygen don't want you. Oxygen don't love you. So why don't you just come over and we'll give you a place to hang out, and we'll treat you a little bit better than that oxygen does. And you know what the hydrogen does? Okay. That's what he does. All right, so this gets removed, and then we have those double bonds that are, or that single bond right there that's a free set of electrons, and that oxygen's electronegative, it's electron greedy, and it goes yum, 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 and it eats all of those electrons up. So when it does this, what we have happen, I'm going to write it on the next line, I'm running out of room, is a CH3 group that had a CH and a double bond CH2. Okay? So that double bond has cleaved. Two sites of attachment open up, one there and one there. And this is pulling the hydrogen off first. Markovnikov's rule happens. Markovnikov's rule says that hydrogen, if it does go on, it's going to set some ground rules first. And it's going to go, listen, I'm picky, I'm clicky. So if you want me to come onto your molecule, that's fine. I'll attach. But I'm going to be very particular on which carbon gets me. And to the right-hand side, you've got more hydrogen. So this is going to turn into a CH3. That's where that extra hydrogen is going to go. And now we have a carbocation that forms to the left-hand side. Well, that forms a carbocation. It's the more stable carbocation out of the two. If it went right-handed, that's a primary. Right now, it's a secondary. That's why Markovnikov rule worked. Well, in addition to that, we've got this carbocation now. And now this molecule feels a little bit better about itself. And it goes, phew, you know, I got rid of that hydrogen. It was just pulling me down. I mean, there's no way that I could have kept 3 up and going. So I got rid of it. I'm back to normal. Thank goodness we can go back to where we were. And then oxygen looks out its window and it probably sees its neighbor jogging by with his shirt off and says, whoa, wait a minute. I didn't realize that was there. And this oxygen looks at that carbocation and it opens up the window and says, hey, come here for a second. I need to know you a little bit better. Could you imagine if that's really how real life was? It probably is in some places. So this carbocation is now positive, and this electron-dense oxygen is my negative piece. And this oxygen is going to make the first move. And it's going to go to this jogger, and it's going to say, hey, you know, I think I got what you want, and you have what I want. So why don't we just get together and we just make this easy for both of us? And that carbocation says, all right, that's fine. Not a big deal. Little does it know that that alcohol group, well, it was ripped of the hydrogen due to that shirtless jogger maybe in the beginning anyway. Okay, so if these two things come together, we get a CH3 and a CH and a CH3 that's here. This is where that carbocation was located, and now this whole thing goes on. We get an oxygen with a hydrogen, and we also get a CH3 that is on that oxygen as well. The whole group goes on, every bit of it. And now that poor oxygen did not learn from its first mistake. And you know, that oxygen says, I did it again. I did it again. I've got 3 bonds and I only wanted 2 and I had to step into this and I got that third one and now I don't want that third one. What's wrong with me? So this is the conversation that alcohol has with itself. Because at this point, it's now positive again. It's 3 bonds. The formal charge is a positive 1. Well, good news. Good news, just like before. There's more than one alcohol molecule that's around. So there is another CH3OH out there somewhere that is behaving just like that other one is. And that is a negative source. And that negative source will say, hey, I know you're in a predicament. You know, you made this stupid mistake again. You got into a relationship with 3 people at once. I told you not to do this. I told you not to do it. So I'm going to come in and I'm going to fix you. So this oxygen says I'm negative, and therefore I'm going to pull this hydrogen off because those are the disposable ones every single time. The electrons between the O and the H then go up to that oxygen, and that oxygen's electronegative and it wants them anyway, and that takes care of the positive charge and it makes it neutral. And now the problem is that that person that scolded that 3-way happening here is now in a 3-way of its own. Little did it know. So what we end up with a product is a CH3, CH, CH3, and then off of this is an O with a CH3 molecule. That is how this structure begins to form. In addition to that, we then regenerate this CH3OH with an extra hydrogen that is positive. That is a protonated alcohol. And folks, this circles us all the way up to the very beginning again. So by definition, this is a catalyst, and that is why it fits that definition. All right, so one more time. Let's review. We have an alkene. This alkene cannot react with just an alcohol. No reaction will happen. In order for that to happen, we have to protonate the alcohol, and that protonation comes from some type of acid. We're seeing that down here in the very bottom. So we protonate the alcohol, and then we use the protonated alcohol up here at the top to react with the double bond, the alkene. The alkene rips the hydrogen off first, and hydrogen plays with other hydrogens. It forms a carbocation. That carbocation then attracts the alcohol group into it, and when that happens, the whole thing gets attached. The alcohol is overwhelmed, something's got to give, and another alcohol group comes in to save the buddy. And it pulls that hydrogen off so that this, what was an alcohol, can now really be happy in form of an ether, an ROR group. And that is my ether functional group right there. So we've just made an ether as a product. And those are the mechanism steps that are associated with this reaction. Now, folks, just like before I said, sometimes they focus questions on mechanism. Now you know the steps of the mechanism and the order of the process that happens, but sometimes they just focus questions on just product formation. That's all that they do. So if you look, what we've done is that we've taken methanol, which is CH3OH, we've split it down the middle, and we've added hydrogen onto one side, CH3, and then we added the OCH3 to the other, and that's what we got on our middle carbon at spot number 2, the OCH3. That's where they're coming from. So that is a very short-handed way to figure out what types of products are going to form, but I at least have to go with the mechanisms for you. Not every single one of these I'll do a mechanism for, but some of these in the very beginning I will, because you need to get used to them. You need to get used to what those curvy arrows really represent. All right, so now let's look at some of the examples. All right, so here's an example. Number 1, give the major product of each of the following reactions. All right, not a big deal. So it looks like I take alkene and I react it with HCl. Yeah, it does. They're kind of jumbling them all up together just to keep you on your game. That's what they're doing. Okay, so this is not a problem here. I've got 3 carbons in a row. So 1, 2, 3. And then off of that second carbon, I've got another carbon there, a methyl group. This double bond's going to break. 2 sides of attachment open up. Hydrogen goes on one side, so that goes here because it plays with other H's. It follows Markovnikov's rule. And chlorine goes on to the other spot. So chlorine is actually going to go there. So there's the product formation. Okay, there we go. That's all there is to it. There's the addition of HCl to that alkene. If I wanted to name that alkene, how would I do it? 3 carbon is the longest chain. 1, 2, 3. So that's a propane. On carbon number 2, I've got a chloro. And on carbon number 2, I have a methyl. So 2 chloro, 2 methyl propane. If I look at this starting reagent, what do I name it? 1, 2, 3 is the longest carbon chain. This is propene. This is 1 propene, because that's where my double bond is at. It's closest to the end. And this is carbon number 2. So on carbon number 2, I have a methyl. So 2 methyl propene. Is this a cis and trans? The answer is no. The carbon to the left, it doesn't have any hydrogens on it. It's a methyl group and a methyl group. I can't use cis and trans. Is it E or Z? The answer is no. And the reason is because it's a methyl group and a methyl group. They're the same. I can't rank one higher priority over the other. So 2-methylpropene reacts with hydrochloric acid to give us 2-chloro, 2-methylpropane. Look at there. Wasn't that fancy? All right, let's take a look at the next example. And here I'm just going to do a clean sheet. That way this stuff doesn't get all jumbled up. We get CH3, carbon, CH3 that points up, double bond CH2. And we're going to react HBr to this. So they want to know what product would form. Okay, well, what product would form? The double bond breaks. So I'm just going to redraw that just so I can show that process happening. That way it's a good visual for you at least. So this double bond breaks. 2 sides of attachment open up here and here. This gets split. Hydrogen adds on first. Markovnikov rule gets followed. So out of the 2 choices, it goes here to the right-hand side. This one has 2 hydrogens. That one doesn't have any. All right, well, I'll simplify this up. I'll get rid of this. This is a CH2, but now it's a CH3. Carbocation form, and Br goes there. If I wanted to name it, 2-bromo, 2-methyl-propane. And we know what the name of the starting reagent is already. It's the same one. All right, number 3. Number 3 is going to use the same starting material, 2-methyl-propene, so CH3, carbon, CH3, double bond, CH2. And this time they're going to react water with H2SO4. They want to know what products formed. That's okay. I got this. You got this too. You got to keep in mind it's protonated, so that's good. If that acid was not there, there would be no reaction. At the same time, you also have to understand that this water can also be looked at as HOH, because that's H2O as well, just written a different way. So that makes my job a little bit easier. I'll rewrite the starting reagent there. Guess what's going to happen? Double bond breaks. 2 sides of attachment open up. There and there. H goes on 1, just like before. Which is going to go to the right-hand side. That's where its click is at. So CH3 gets formed. And folks, what we have left over is OH group. And there we go. I've made an alcohol. That's what this reaction does. If I wanted to name the alcohol, I could. It's still propane, right? Propane. Well, I dropped the E, and I add OL for alcohol. Where does that alcohol happen? It happens at carbon number 2. And then at carbon number 2, I also have a methyl group. So 2-methyl, 2-propanol. If I wanted to common name this, I could. Do you know what the common name would be? Well, this alcohol is on a tertiary carbon, isn't it? And it's CH3, CH3, CH3. It's one of those common names that we learned back in the day. And this was called tert-butyl. So tert, of course, for tertiary, butyl because there's 4 carbons in total, and the word alcohol. Tert-butyl alcohol. Ha! Look at there. Did it again. Pulled some of that old material back into something new. All right, one more. CH3, carbon, double bond, CH2, and then CH3 there. Same starting reagent, but this time I'm adding methanol and H2SO4. I don't want you to get comfortable with this, though. I'm changing this. I'm not going to do this as far as the example goes. I'm doing CH3, CH2. Just to show you that we can. I don't want you to get used to methanol. Any alcohol will work. All right, so what forms? Well, you know what I'm going to do. I'm going to rewrite this starting product or reagent again. All right, and that's where I'm going to go with it. Well, in this reaction, double bond breaks. There we go. 2 sites of attachment open up. Go figure. Seems like I'm saying the same thing over and over, doesn't it? If so, that's good because that means you're learning it. And then if I look at this alcohol group, I don't need to think about mechanism. I just need to look at this alcohol group and split it right there and say H goes on first. Well, H plays with other H's just like before. There we go. Markovnikov's rule is followed. CH3 goes on the end. That opens up this side of attachment. That's where my carbocation is. That carbocation will take over everything else, and that is the oxygen that I cleaved. And that will carry with it a CH2 and a CH3. And there's a product. Folks, they're all very similar. Every one of them follow Markovnikov's rule. Every one of them follow breaking the double bond. Every one of them follow forming the most stable carbocation. It's the same template. That's really the take-home message here. It's the same template. What if you had to name this? We can IUPAC it the longest carbon chain. All right, so the longest carbon chain here is going to be this 3-carbon chain. So this is a propane. On carbon number 2, I have this methyl group. And then on carbon number 2, I have this OCH2CH3 group. Do you remember what we called that? Well, if we have to name this O, we know that the word oxy has to be in it. And this 2-carbon chain would be called ethyl. So we just put those 2 pieces together and call it ethoxy. So this is 2-ethoxy, 2-methyl propane. That's the IUPAC name. Can we common name it? We can common name this one. How do we do that? I look at this oxygen and I name each thing on each side. So the oxygen here is attached to a tertiary carbon that's the same all the way around. That was a special term that we used, and that was called tert-butyl. And then over here to the right-hand side, it's a 2-carbon system. So this is ethyl, and then we add on the word ether. So just a review, that's all that was. Tert-butyl ethyl ether, or IUPAC 2-ethoxy 2-methyl propane. I always like to bring those back into our discussion because it's very easy to forget some of those things as we go further and further into this material. And I never really want you to forget some of that stuff. All right? Okay, so that's where this video is going to stop. In the next one, I'm going to do more examples, though. Okay, I'm going to do more examples, and it's just a different perspective on these reactions so you can get more comfortable with them. We've got 3 different reactions that we're juggling now at this point, if you've noticed. We've got the H halogen, okay, and then we have the water addition, and then we have the alcohol addition. And those are the three that we're going to juggle in the next video as well with those example problems. So come back. We're going to continue on this discussion. Now's not a good time to stop. If you need a breather, go take one. But come back, and then we'll pick this up where we've left off, and we'll just look at these reactions going backward a little bit, just to give you more experience with the synthesis types of problems.